Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, in this moment we can meet again in this Zoom meeting, and we can study together about competitive programming. And let's continue our discussion about graph or about depth first search. And before we start our discussion, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Rabbana zidna ilma warzuqna fahma. Rabbi ishrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. Okay. So before we continue, in the past meeting, I already implement problem N. And then let's check our implementation. So after I try to submit this solution, and unfortunately, it is still got wrong answer from this test case. And from this test case, I realized that the bug is not in the pre-coloring, but in the dynamic programming. So let's try to analyze it. So let's draw a graph starting from node 1. So this is node 1, 1 connected with 3, 3 connected with 2, and then 2 connected with 10, 10 connected with 6 and 7, 6 connected with 5, 5 connected with 9, 9 connected with 4 and 8. All right. Yes, I think the graph is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Maybe let's make it prettier. Let's move it to the upside. This is 9, 4, and 8. And how about the color? So the color is like this. This is 1, 0, and then 2, 3, 0, and then 1, and then 4, and then 5, and then 1. All right, so no need to do in the first coloring. So when we try to output after the coloring, the array is still same. All right, so how about the dynamic programming? Maybe let's output the color. The color is just same, right? Just the same array, since but one is already connected into one component. Alright, so then I try to output the dynamic programming, and let's see. The dynamic programming for 8. Okay, let's write a number here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or let's output in this way. Alright, so for 8, of course, we can only make it colored, so we cannot make it is uncolored, so just 0, 1, like this. Okay, this is correct, and 4 is also correct. How about 9? 9 is also correct, because we must cut this and cut this, so this is the only answer. Alright, so how about 3? Sorry, 5. This is also only one ways. And then for 6, there are two ways. One way is if we want to make it colored, so don't cut this. But if we want to cut this, then it is uncolored. Okay, 6 is correct. How about 7? 7 is correct. How about 10? 10, of course, we cannot make it uncolored since it is colored. And there are two ways between cutting this or this. So either cut this or cut this. Alright. Yes, there are two ways. It is still correct. Okay. And then the rest is just multiplying between, wait, we cannot cut this at all, right? And let me try to open my submission so we can check what is the intended answer. The intended answer should be 2, right? So because we can just choose whether we cut here or here, and the other one is just always keep uncut. All right. After that, for 2, it is still 0, 2. It is correct. But how about 3? 3, I think should be 0, 2 as well. Or at least, okay, we can cut here, become 0, but it is should be colored, so the output is TP11. Alright, so for 3, if we don't cut this become colored, but the result is not like this. Okay, so the formula is incorrect. Let's check in the DFS. When there is an uncolored node and then in the child, the TP is 0 and 2. So the results will be 2 and 2, right? Let's check. TP now 1 is equal to 1 initially. And then just check for each child. TP1 multiplied by 2. Alright, so now TP0 equal to 2. After that, since A now is equal to 0 and TP now 1, wait, yes, TP now 1 is not equal to 0. Okay, this is initially like this. So TP0 equal to TP1 and then TP1 equal to 0. What else? We will iterate for our child. We will add TP1 by TP now 0 times TP child 1 times 1 hour wait 1 hour 2. Okay, so P equal to 2, right? Maybe I miss create the exponentation. Modulo is like this, okay? And that's a prime number. What if I change it into this? Is correct or not? Okay, the answer is 2. All right. But what if I use exponentation? Why it is incorrect? What if I create bracket here? There's an effect because modulo and multiply is in the same level, in the same priority. If y equal to 0, then return 1, okay. R is equal to expo x times x modulo mod to the power of y divided by 2. Okay, I think no need to do this, right? Sorry. All right, so let's check again. Okay, so the pack is here in the expo. So let's try to submit again. Okay. Is there any question about this? Have you tried to implement or try to find the idea? And I have add you some problems, add you two problems, problem Z and double A. And two of you, Rafiullah and Faisal, already solved it. Okay, sorry. Maybe Faisal and Raza. So both of them are seniors, right? Maybe seniors ever discuss about this problem. Okay, I think we will discuss these two problems after it. Alright, I think it is accepted. Okay, accepted. Alhamdulillah. Okay, so you already discussed this, right? Already solved this? No, okay. But seniors already solved them or solved this. Alright, so have you read this problem? Alright, I see. And I put this problem here because the solution is just DFS. That's why I put it here. Even this is IOI problem. Have you read this problem? This IOI is that much simple nowadays? I don't think so. The solution is simple, but on contest, not much got accepted in this problem. So let's check. Let's check the scoreboard. Yes, only DFS, but the idea is so secret. All right, but the implementation only DFS. So just try to read this at first, and let's see in the scoreboard of IOI. Let's see for problem split. Okay, so only 1, 2, 3, 4, 5, 6. Only 6 got accepted in this problem. And me, I just got 14, and majority of the participants got 14. Sorry, 40. Even until 157, I think. 157 got 40. And only 10 participants get more than 40. All right. But the solution is quite short and only using DFS. Okay, so let's see the problem. given n nodes, all right, n nodes and m undirected edges. So this is undirected graph. Given undirected graph with n nodes and m edges. And this is connected graph, possible to travel. So undirected, connected. Okay. And then actually the problem is also simple, but it is hard to find the idea to solve this. So there is a character who want to visit the attraction in 3 days. So let's say we want to divide the graph into three groups. And the first group, there are A attraction or A nodes. This is the first group. And the second group, B nodes. And the third group, C nodes. And we know A plus B plus C equal to N. So it means we must take all of the nodes. Okay, we going to partition the attractions. All right. And every node shall put into one of the groups. Okay, and cannot put into more than one groups. All right. Yes, it is easy to understand, I think. And then the most important rule is at least 2 out of the 3 sets are connected. So for example, this is connected, and this is disconnected. It is okay. Or this is connected, and this is disconnected. It is also okay. What if both of them are connected? It is also allowed. But actually 2 of them is okay. But if the connected one only A, it is prohibited. All right. Yes, the problem is just like that. And we want to find the attraction. Okay. So this is quite simple. Given undirected connected graph, and we want to find the partition consists of A nodes, B nodes, and C nodes, and 2 of the groups shall be connected. All right. And then given N and also A, B, C, of course, A plus B plus C equal to N. And then given the edges, given M edges connecting P and Q. All right. As usual, IOA problem is functional, so we shall write this function. And no need to write main function. Okay. So is the problem understood? Simple, right? And so is the solution, but not for the idea. Okay, this is one of the example. Given a graph, undirected connected graph, we want to split into 4 to 3. So just make the first group like this, and then the second group like this, and then the third group like this. All right. Is the first group connected? How do you think? The first group connected or not? Yes. How about the second group? Okay, this is the second group, consists of 2 nodes. Yes, connected as well. How about the third group? Not connected. Okay. But it is allowed. So it just need to connect two groups. Alright. So just return an array or a vector that showing the groups. For example, 1 and 0 from the first group, and then 3 from the first group as well, and 7 from the first group. Alright. Okay. Is there any question about the problem? Okay. If it is impossible, so just return a vector with size n that consists of 0. It is if impossible, just like when we see out -1. But because this is functional, so we should return a function, sorry, return a vector. So just return 0, 0, 0, 0, 0. All right. Okay. Do you know why this case is impossible? We want to divide into 2, 2, and 2. How to do that? Can we split them into 2, 2, 2? This is valid or not? Is this valid answer? No. Why? Because only one group is connected. Yes, only one group is connected and the other two is not connected. But the rule is at least two should be connected. So it is impossible to do that. Because if we put this, so the other node is not connected. All right. And the constraint is n 100,000 m 200,000 a plus b plus c equal to n. All right. There is no multiple edges and the graph is connected and there is no self loop. All right. It is normal. Okay. So let's check how to solve the first subtask. Do you know how to solve it? We have to find a path of length. Okay. We have to find a path of length minimum between. Okay, yes. Okay, so if we got a path with size a plus b, for example, maybe let's generalize a less than b less than c, less than or equal, without loss of generalization. Right. Let's assume a less than or equal to b less than or equal to c. So if we got a path with length a plus b, yes, we can solve this. Just create a group like this, right? And the other node come into C. Okay, yes, that's one of the good observation. So from that observation, can we solve first subtask? Do you know what this constraint means? What does it means? A chain at most 2 edge for each node. Yes, yes, we know at most. So the graph become inward form. Okay, one of the possibilities is a chain. Is there any other possibilities? Cycle, that's it. Cycle is also satisfying this constraint, right? Yes. So can we, or can you solve this using the previous idea? Actually, if it is cycle, so just cut one of them, so become a chain, right? After cut a chain with length n, what shall we do? Yes, it is always possible. Just take A here, take B here, take C here, right? So both of them is connected. So it is so easy for getting 7 points. If almost all participant get at least 7. Okay, yes. All right. After that, let's check. What if A is equal to 1? How do you think? How to solve this? What does it mean? A equal to 1. A graph consists of one node. What is the property of it? Yes, always connected. All right. So now A is always connected. So we just need to consider for B and C. Just make one of them connected and one of them up to you. Yes, this is always possible as well. How to find the configuration? Remove any node U and check the size of its component. What if in this problem 1, 2, 3 like this? Remove any node U. Let's say node 0. Check the size of each component. Each component consists of one node only. Okay, yes. We must got an idea. We can run a DFS and use the first P nodes. All right, yes. Okay, here. Okay, sir. Check for all nodes. But if we check for all nodes, maybe it is n square. Okay, so just do BFS, right? Until we got the first P nodes. So this is connected. So for C, it is not connected, no problem. And A, because it is only consists of one node, it is always connected. All right, we can solve this using BFS, right? What if we use DFS? Is this correct or not? Yes, also okay. So no problem if we use DFS. So just got the first P, and this is always connected. So just put A and C for the rest nodes. All right, so you got the first and second problem. Sorry, first and second subtask. So how about the third subtask? What does it mean? It is 3, yes. And majority of the metal is got 40 point. So it is still easy, but subtask 4 and 5 is quite hard. Okay, so how to solve the third subtask? How do you think if the graph is 3? There is no cycle here. Okay, is there any idea? Rerouting, yes, maybe. So for each node, what shall we do? What shall we do for each nodes? Or for example, for when this is the root, then how to check whether we can make a partition or not? The nodes and the endpoint of the geometry, the tree. So let's imagine it is diameter. So some nodes in the left, some nodes in the right. So run DFS from both nodes. Of course, we will cut this and this, right? And also the middle node. Sometimes we cut the middle node. The middle node is go here or here. All right. What shall we do after we do PFS from A and B? Okay. Maybe we want to get A here and B here, right? Is it always possible? What if the graph is star graph? So this is the diameter, right? We want to do PFS for A, and for B, we cannot cut it, right? So when the answer is impossible, when A and B is intersect, then what if the graph is, wait, yes, let's try to create this graph. For example, A is equal to 1, 2, 3, 4. A is 4, B is 4, C is 4. Wait, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's remove it 1. All right, All right, ABC is 4. Is this impossible? If we do PFS and then do PFS, it is intersect. But this is impossible or not? How do you think? Impossible or possible? Okay, it is possible because we can cut this and this. Alright. And the rest is this. This is not connected, but it's still okay. Alright, so let's find the other idea. What do you think? Right. How about the rerouting? Isn't that a good idea? Find a node U such that it is a sub-tree size. Sorry, that its sub-tree size is at least A and its child size is less than A. Okay, so for example, there is a specific node U. Its sub-tree size is greater than or equal to A, and all the child is less than A. Then remove A from the graph. So do you mean remove U? Okay, yes. Remove the U. Remove U from the graph and check that component is at least size A or not. Of course, for this child, it is less than A. So the only possible case is this, greater than or equal to A. Is it correct? Yes. If this is greater than or equal to A, what shall we do? If all of them less than A, then what shall we do? Then possible, otherwise not. That's it. Yes, this is impossible. Why? Because if we want to get a component with size A, where A is the minimum of the three values, if we want to get A, it means we shall choose this node, right? We shall choose this node. But if this node is chosen, then we cannot create a component with size B, right? Why? Because if this is chosen, the component is less than A, and of course also less than B. Alright, yes, so in this case, this is impossible. How about this? Can we always solve this? How to create a partition? Do you know how to create a partition from this? how to create a component with A and component with B, and the rest is for C. Then which node we should take? Is it always possible or sometimes it is not possible? What if, for example, A is 10 and then B is 20? So this is just 9, 9, 9, and then this is just 10. Is this always possible? Okay. If U sub 3 size is greater or equal to B, then yes. Sign 2 in B. Yes, that's it. This is always possible. Why? Do you know why? So just check whether this is greater than or equal to P or not. So there are two cases, greater than or equal to P or less than P. Wait, or check this. Check this. Is this greater than or equal to P or less than P? If this sub 3 greater than or equal to P, then just choose P from here and choose A from here. But what if less than P? We know this node is greater than or equal to A, right? Because we find such nodes. U is from that node, a node that satisfying this. So we can choose A here. And is this always greater than or equal to P? The answer is yes. How to prove that? So if this is less than or equal to P, it means this is n minus P, right? And do you know what is the maximum value of P? So this is n minus P. Is n minus P always greater than or equal to P? Always or not? Is it possible that n minus P less than P as well? So this is less than P and this is less than P. So the answer is not, because P is always less than half. Because P is less than half, so less than P means less than half. So the other component always greater than half. And because P is less than half, so this component always greater than P. Okay, you got it? Do you know why P always less than n divided by 2? Why? Just prove it by contradiction. Yes, that's it. Because P always less than or equal to C. If P more than or equal to half, then yes, that's it. Then it means P greater than C. So it is contradict. Alright. So now we can solve subtest 3. So do we need rerouting? I think not. Wait, how to find such node U? By simple DFS, that's it. So just find the subtree size of each node and just go to the child when the subtree size is still greater than or equal to a. If there is a child that is still greater than or equal to a, so just go there. But if now there is no child greater than or equal to a, so just stop at this node. Yes, just like centroid, but a, not n divided by 2. Okay, yes, that's correct. So let's continue. What if the graph is not a tree? If the graph is not a tree, what shall we do? Can we use that idea for a specific node? So just divide the components. What if all of them is less than a? How do you think? What if all of the group less than a? For example, let's use this sample. If we choose this, then yes, actually this is just from a group, right? If it is just become a group, then don't do that. Let's choose this node. Then this node form a group, right? It's not form a groups. Group consists of 3, and then here group consists of 1, group consists of 1, group consists of 1, and then group consists of 3. What shall we do after we cut this? For example, a equal to 2, b equal to 3. There are two groups of 1. Okay, yes, sorry. Only 2. Then, is this possible? Is there any configuration? Yes, of course. Just take 2 here and take 3 here, right? Alright. So, do you know what I mean? We will choose a special node and then just create a group of connected nodes and then group of connected nodes if we remove the U, just like the idea from Abdullah. If we remove U, then become some component. What if both of the component the size is less than A? So this is possible or not? Possible. Impossible. Yes, just like the previous. Maybe possible. Wait. Yes, cycle can be there, but cycle only exists here. Cannot connect between component, because if connect between component, it means it is in one component, right? Right. If there are two nodes connecting you here, it is counted as one component. All right. Yes. Then it is impossible because this is if we remove u, both of them less than a. So if we want to take p, of course we solve take u, right? And then we cannot get a from any component. All right. So it is impossible. And then what if there is a value that greater than or equal to a? Then what shall we do? So there are two cases. There is no greater than or equal to a, or there is at least one. Okay. Exists at least one or doesn't exist. If doesn't exist, then always impossible. What if there is at least one component greater than or equal to a? Then what shall we do? Is it always possible? Always possible, yes. Just use the previous idea, right? Just use the previous idea. What does it mean? Just check whether this is greater than or equal to p or not, or less than p. If this is greater than or equal to p, so just use p here and a here. What if this is less than p? If this is less than p, it means this is greater than or equal to p. Wait, but what if this is not? But what if this is less than a? Is it possible? Wait, so there are two cases when the combined component greater than or equal to p or less than p. If this is greater than or equal to p, then all right, we can create p here and a here. So now we want to find the solution for the case where this size is less than p. Is it possible that this is less than a as well? Okay, I think if this is less than a, so just choose another node, right? Just choose another node for u. Don't choose u here. Is it always possible? Choose another u, and then just check. Yes, I think like that. Just choose a value u that is greater than or equal to a. All right. So now can we solve this subtask after we got this observation? Yes. So just try for all nodes. Try for all nodes, and then just find the connected component for another node, and then check whether there is a component that less greater than or equal to a, and then the other is greater than or equal to a as well. If there is not like that, so just create a configuration because one of them shall be greater than or equal to p. All right, but if there is no, or this is greater than or equal to a but the other is less than a, so just find the other root. If there is no root like that, so just return impossible. All right, so now we got 64 point. And then how to solve the whole problem? Is there any idea to solve this? Just combine these two ideas. Yes, that's it. Just extend the idea. So the curve is not 3, all right? Not 3. Not that this is not 3. Sometimes there are cycles in this graph. But let's do DFS. Just create a DFS tree and then just find the subtree size and find just like centroid but greater than or equal to a and all of the child less than a. After that, what shall we do? After we got a node that the subtree size is greater than or equal to a, and then but child is less than a. Then there are two cases, right? Whether this is whether the rest of the component is greater than or equal to a. Okay, for this case, it is possible, right? We can create a partition here. And then what if this is less than a? What shall we do? You know, for this component, they cannot connect each other. There is no edge connecting both component here. Why? Because if this is connecting, so when we do DFS, we will DFS until here, right? Okay, so there is no edge connecting between two groups here. But is it possible a group connecting with this? Simple or not? No, why? What if there is a graph like this? Actually, there is an edge here, but this is already visited, so we skip it, right? In the DFS tree. But actually, this component can connect with the rest component, right? How do you think? Do you agree with that? So let me state a conclusion, and do you agree with this or not? We already create some groups, and we know from this group cannot connect with each other directly. There is no edge between this group. There is no direct edge between this group. All right. But sometimes there is a direct edge between this group to some of the group here. Do you agree with this? Yes, all right. So for this case, it is not always impossible, but we have to check, right? Whether is there any component like this. Okay, so sometimes we can connect this here, connect this here, so the size become greater. All right, so now there are two cases here. The case where after we connect all of them, the size is still less than A. Or for example, there is no component can connect with this, so the size is still less than A. So what does it mean? It means it is impossible, right? Why? Because we already know the real component. We already know the component for all nodes other than U. And both of them is less than A, so it is impossible. Yes. All right. Because we have to choose U. Yes, that's correct. And what if after we connect all of them greater than A? Just like the previous idea, right? Greater than A. But if after we put all of them still greater than A, sorry, already greater than or equal to A, there are two cases. When then what is the rest of the size here? If the rest of the size, sorry, the subtree of U, the rest size of subtree U, after we remove this and this, for example, if this is greater than B, all right, so it means we can take B here and A here. And the other case is when the rest is still greater than or equal to A. So just take A here and we always can take B here. Is it correct? Because it is greater than or equal to A but less than B. So this component must be greater than or equal to B. But what if the rest is less than A? What shall we do? Then the idea is like this. Please don't connect all of the nodes. For example, we just connect with this, but not this. So the rest is still greater than or equal to A. All right. So just connect this. Just connect some group that can connect with the upside. But when the size is already greater than or equal to A, please stop. Don't continue this. All right. So don't use all of them, but just use some of them so that this is greater than or equal to A. If we do that, so this case is impossible. Do you know why? Because there is an observation that A is always less than or equal to n divided by 3. Do you agree with this? A less than or equal to n divided by 3. Can you prove that? I think it is easy to prove that. Yes, okay. Just prove by contradiction. If n is greater than n divided by, A greater than n divided by 3, it means B and C also greater than n divided by 3, right? So the sum is greater than n. and it is impossible. All right, so let's create a number line, for example, a number line from 0 to n, and then let's make it a, and then this is n minus a. You know, the rest of it always greater than a. Is it correct? Because a is less than or equal to n divided by 3. All right. So when we are facing a case where the upside is still less than a, all right, initially still less than a, and then we add group by group, for example, add, then add, and then add, and so on, until greater than or equal to a. Then it is always less than n minus a, right? Never exceed n minus a. So there is no case where we add here and then jump directly here, skipping all of this. It is impossible. Why? Because all groups here are always less than a, right? But the gap between this and this is greater than a. So when we jump less than a, never exceed this point. Do you know what I mean? It means this group, if it is cannot exceed a, so okay, it is impossible. But if it is can exceed a, then the size is always less than n minus a, right? If this is less than n minus a, it means this group always greater than or equal to a. So we remove this case, right? There is no this case. So just solve for this case only. And both of them is possible. So it is always possible. All right. You got it? So let me conclude the solution. Just at first, the first step is just find any u. Just any u, not all u. Not a specific u, but any u is allowed for any u. Any u that when we do DFS on graph, if we do DFS or creating a DFS tree and then find the subtree size, then just find a node that greater than or equal to a, and then all the child is less than or equal, sorry, less than a. So this is that u. All right, and this node always exists, and we can just find it in just on complexity, right? After that, what should we do? Just check the size of the rest. So n minus sub u like this. All right. And then, okay, just check whether there is a group that connecting with upside. We can check them in on as well. Just iterate for all edges, right? So let's check while this group, for example, let's say the size is s. So while s is still less than a, just find a group that can connect to this upside. All right. If there is no group can connect the upside, and S is still less than A, so just see out impossible. Just return impossible. But if this is already greater than or equal to A, then okay, we already get a component greater than or equal to A, and then this is also greater than or equal to A. Then just check which one is greater than or equal to B. If this is greater than or equal to B, just create B here and create A here. If not, then it means this is greater than or equal to B. Just create B here and A here. Alright. So the total complexity is just ON. And the main algorithm is only DFS. I think there is no another algorithm except DFS and greedy, or not greedy, DFS plus observation. Alright. Is there any question about this? So just try to solve it. I think you have solved this before. Yes, I just use DFS. And the solution is just DFS. This is DFS to find U, and then this is DFS to color the group. Because we need to find the configuration, right? So just use DFS to coloring them into 3 colors. Alright. Is it understood? So how do you think this is simple or not? And then easy or not? Is this simple and easy, or easy but complicated, or simple but yes, or simple but hard, or hard and complicated? I think it is simple but complicated. So it can be, yes, it is paragraph, right? Only 6 of the participants solve this. Right. So let's move to the previous one. This the solution is also DFS. Let's check. Given a tree, right? Given a tree, so the parent of node I is pi, and 1 is the root of the graph. What else? Wait, constructor cup. Where it is? Or where is it? Is it in code force or alright? So I don't participate, but maybe I want to see the problem later. Okay, thank you for the information. Yes. Is this the problem? Or there were 12? Where is it? Okay, thank you. Can I repeat the problem? Wait, I am not in the group. All right, no problem. So how to register it? Okay, so I will register it later. Let's bookmark this. Okay. All right. Thank you for the information. And let's back to the problem. So even, sorry, this is pi, that is the number of child. Pi is equal to the number of child. And then there is a rule like this. So each node or each person can be agree or disagree. Either agree or disagree. All right. Then the rule is like this. If di or exactly di, wait, yes, exactly di child must cast different vote. So for example, this is agree. So it means the child, for example, di is equal to 2, then it means two of them should be disagree and the other is agree. All right. Then for example here t is equal to 1. So one of them should be agree and the other is disagree. All right. And ti is given. After that, every member has an influence level wi, and then the dominance value is equal to the difference between agree and disagree. So for example, this node are agree, so just find the sum of the influence level, and then the rest is disagree, find the influence level, and then find the difference. And we want to maximize the dominance level. Then how to calculate it? So given a tree like this, given an influence level, and then given d, how many number of child must be in different, or yes, different state with the parent. All right, and then we want to find the maximum dominance level. Okay, so just think about the solution, or you can find the idea from the subtest. And I want to go to the toilet first, so just think the idea. Okay, let's continue. Do you got any idea? Okay, so it means we ever discussed it before. Yes, I forgot about that. So it means you already solved the solve it. So let's remove it. Okay, thank you again for the notice. So let's continue the next problem after n. Alright, for problem O, I think two of you already got accepted. So the problem is given a tree and we want to put a number for each node, just like put a permutation, right? Put a permutation to the node. For example, put a permutation like this, 1 here, 2 here, 3 here, and so on. And we want to create a list using this way. So at first, choose any leaf. For example, we choose this leaf. After we remove this, if in the upside is less than this, so just make the value become this. All right. So if we take this, the value is 2 as well. And then if we put 4 here, for example, so this is become 4. And then if we take this 6, and then this is 4, and then 1. And after we got a value, our points or our value is equal to the longest non-decreasing subsequence like this, 2, 2, 4, 4. So the result is 4. We want to maximize the longest non-decreasing subsequence. All right. Okay. So how to assign this if we want to make it optimal, want to maximize this? So, if we put 1 here, we will cut from this until this, right? Even we can cut until this actually. But we can also put another value, for example, 2 here. So we can cut 2 here. But when 1 cannot exit until here, because if we want to take 1 here, we shall take this first, right? So just put only until here. All right. And we also cannot take here because if we make 3 here, if you want to take 2, it means we should take this first. All right. So we are just choosing some chain, right? Creating some chain so that for each head of the chain, one cannot be the ancestor of the others. All right. Okay. For example, we will choose this as the head. So it is allowed. So the result is 4. Or we take this and this, the result is 4 as well. But if we take this, the result is only 3, and so on. If we take this and this, the result is only 3. All right. So how to solve this? Just use dynamic programming on 3 as well. Is it correct? No need to DFS. PI maximum length of sorted array. Maximum length if of sorted array if we use only sub 3 I. Yes, that's it. We no need to do DFS because we know that the parent always less than, sorry. Yes, the parent is always less than that. So actually we want to do DB on 3, but no need to do DFS, right? Just iterate from n to 1. Is it what you mean? Just use DB like this. Yes, alright. So I agree with that. I agree with you. So because pi is always less than I, so okay. So all of the child must be with the greater value. So DP already obtained, the value already obtained. So we can gather the information. So The value of dp is equal to the maximum between two cases. So there are two cases. The first case is when I is taken, or we will create a chain starting from I. So the result is only the height of I. Alright. The height, not the depth. Okay. After that, the second case. The second case is when we don't take I. It means I is free. So we can take the maximum for each child, right? So sum of TP child. Alright, this is the formula. It is quite simple in the implementation. Okay. Is there any question about problem O? So let's continue to problem B. So for problem B, given a tree and there are some value in its nodes, and the value sometimes negative. So for example, there is a tree and the value sometimes negative. For example, -2, 3, -5, like that. Can be 0 as well. All right. What else? So we want to take two subtrees, two non-intersecting subtrees. For example, this and this. But we cannot take this, right? Since it is intersecting. So just like the previous one, right? We want to take, but not chain here, but subtree. But one cannot be the ancestor of the other one. And we want to maximize the total value. Since it is sometimes negative, so not always taking the child of the root, right? If all of the value is non-negative, so just take for all value. So from root go to the child until there is a branch, right? There is a branch. So just find the sum for each subtrees and then take two of them, right? Take maximum two. But what if it is negative? So just use dynamic programming, right? Just use dynamic programming or just use brute force actually. Just use DFS since the graph is given in this way. Not using parent list but edge list. So just DFS and then for each node it is storing the maximum of all size subtree. Sorry, not size subtree, but sum of subtree. Sum of subtree of all its descendant. So there are two value we need to count. The first one is subtree size. Of course, a subtree is equal to 1 plus total subtree for all child. And then let's say n I is equal to the maximum between sub I and maximum between all sub C for all tile. All right. So for each node, just sort all of the answer of the tile. If the number of tile is less than, sorry, if the number of tile is greater than 1, then just take to maximum, right? All right. Is it correct? Okay. Is there any question about problem B? So let's continue for problem Q. For problem Q, given a tree with n nodes, n minus 1 edges, and given a value here, but the value always positive. Okay. And we want to choose a specific vertex, let's say vertex V. And then we want to maximize the cost. The cost is computed as follows using this formula. And we want to choose any fee and just output the maximum possible cost. So first, if n is small, if n is only 1,000, so we can try to iterate for all nodes, right? And then just find all of the distance using DFS, and then just multiply it by AI. Okay. But do you know how to solve it faster if n is 200,000? What is the idea? Yeah, just use rerouting, right? Just use rerouting. So let's say we already compute all of the costs for each subtrees. How to compute it? Since the formula is like this, so it means we want to find the subtree size, right? And then the cost for subtree I is equal to, you know, 0 times AI, okay, because the distance to I itself is 0, so just multiply by 0. So just no need to count it. And then just find the sum for each cost of the child, right? Cost of the child, and then add it by the sum. I think we need to find the sum of sub3 equal to AI plus sum of the child. Just added by sum. Why? Because for this node, the distance is added by 1, right? For all nodes here, the distance is added by 1. That's why we solve at all of the value multiplied by 1, right? So just add sum here. Okay, so this is the cost. All right, so now we can put the cost. If we choose 1 as the root, just use cost I, right? And then how to know the real cost for each I? Then just do another DFS. For example, this is the first DFS, and then this is the second DFS. Just do rerouting, right? Because this node already got the total value for all node, but this node is still no the subtree only. So we can get the value by using this. Cost of the child is equal to, for example, this is child, this is I. Cost of the child is equal to cos I minus cos child minus sum child. It means it is equal to this subtree, right? So because C already compute all of the subtree here, just add by this, right? So just add by cos I minus cos C plus sum C. What else? Added by sum of this, right? Added by sum of this. What is sum of this? Just add by total sum, or just sum the root. The root is 1 minus the sum of C itself. So total sum other than this. All right. So this is the formula. Because this is cos C added by minus cos C. So we can remove this, right? And then this is minus sum C minus sum C. So just minus 2 times sum C. So if we simplify the formula, become like this. This is not plus but equal. Cos C equal to cos I plus sum 1 minus 2 times sum C. All right, just do this. And now we got all costs. Just find the maximum for all costs. All right. Is there any question about this? All right. I think there are some problem left. And then let's continue to problem R. So this is given a graph, and we want to start at some vertex. Okay. We can start at some vertex, for example, vertex 1. And then we can go to another vertex, right? For example, go here, and then go here, and then go here. And then we will write the value for each visited nodes. So the visited node is 1, 2, 3, 4, right? Okay. So maximum number is 4, right? All right. So the problem is like this. Given n and m, given n nodes with some values, and then m edges 1, 2, 3, 4, 5, 6, 7, and this is directed. And then we want to perform k minus 1 moves. It means we will visit k nodes, right? And we want to maximize the value in the path. All right, so this is one of the example. Can we get 5 here? 1, 2, 3, 4. 1, 2, 3, 4. Wait. 1, 2, 3, 4. Okay, sorry, we want to minimize it. So the value is equal to the maximum number, but we want to make it as small as possible. So 4 is the smallest. Because if we visit this, then the result is 10. If we visit this, then the result is 5. So we will exclude this or avoid them. So we will visit here. All right. And what is the second sample? The second sample is just the same graph, but we need to move 100 times. It means if we avoid this two, we cannot move 100 times, right? Only a finite times. And what if we avoid 10? We also can only visit 5 nodes, right? So we always visit this if we want to move in a loop like this. Or we can also do the loop here. All right, so the result is 10. And then how about this? One can go to 2, and we need to visit 5 nodes, and it is impossible to visit 5 nodes. So just see out -1. And in this graph, the node is just 1, and we need to visit 1 node, so just use this. All right. Okay, that's the problem. Is there any question about problem R? And I think it is already 9 p.m. So let's continue to the next meeting in Tuesday, inshallah. So I think that's all for today. Let's see you again in the next meeting. So let's close our meeting with praying kafaratul majlis. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassalamualaikum ala nabiyyina Muhammadin walhamdulillahirabbil alamin.